You multiply the constant times that, right? So what would this times this be? 4. Right? 4 over n times n would be 4. Agreed? Okay. Plus, okay, now this one. 32 over n squared is a constant, isn't it? It can come out. What's the sum as k equals 1 to n of k? So imagine that's out in front. I'll put it out front right now. 32 over n squared times, so I pulled this out in front. What is the sum of k? That's Gauss. That's the kid. That's the first grader. What was his formula for this? This is n times n plus 1 over 2, right? That is the formula that Gauss came up with for the sum k equals 1 to n of k. It's that right there, right? And then I have plus 64 over n cubed. Again, is treated like a constant. And then what's the formula for sum k equals 1 to n of k squared? N times n plus 1 times 2n plus 1 all over 6.
Can you tell me just real quick how you got 4 at the beginning? I'm sorry, I missed that.
Okay, so when we had this earlier, sum of a constant times n equals to constant times n, right? Sum k equals 1 to n of a constant is just this constant times that, right?
Right.
So like at this point right now, if I told you n was, let's say, 5,
Right.
then this would be 5 and that would be 4/5.
Right.
And so you'd say 4/5 times 5, which would kill off and you just get the 4, right? So as soon as n is like fixed, that's what your sum would be, right? All right, here it is. This is it. We were trying to come up with a formula that would give us the area underneath x squared between 1 and 5 if we used n rectangles. And this is it, right there. Okay, so I'm just going to write it down a little bit different. Let's see, we have formulas 4c plus, can I clean this up at all? At 32 over 2, that's 16, right? So watch this, it's going to be 16, and just bear with me here, n squared plus n over n squared, right? So that's 16, then I distributed the n through. You'll see why I did that in a second. And on this one, can this clean up?
Yeah, we can reduce it to 15 and 2. No, sorry.
32 thirds,
3 and 64.
right? So I'm going to do it this way. I'm going to go 32 on top. What's still on the bottom? I got a 3, got an n cubed. And I actually want to multiply these together. So I maybe have to do this real quick. I've got 2n squared plus n plus 2n plus 1. So 2n squared plus 3n plus 1. Then I hit it with an n. So my top here should be 2n cubed plus 3n squared plus n. Yes?
Cancel the n's on the, it's like 32 over n squared and then n to the n plus 1. Can you cancel the n? That's
I could have gotten rid of one n there. Yes, I could have. But you'll see it's not going to matter in a minute. All right, there it is, everyone. There's our formula. So do you remember what the area was when we had one rectangle? Was it 100? Was it 100? Okay, if we plug 1 in here, we should get 100. Let's just check it. If I plug 1 in here, what do I get? 2. So this is going to be 2 times 16. So I'm going to get 4 plus 16. So 32 plus, let's plug 1 in here. That's going to be 2 plus 3 plus 1. That's 6, right? That's 6 right there. 6 over 3 is 2. That's 64. Is that right? Yeah, that's 100. Now, if I plug n equals 2 in there, what should I get? What was it, 54 or something like that, or 68? And if I plug in 4, I should get 50 something. And if I plug in 1,000, it should give me the area, right? Understand? This formula only works for the function x squared, and it only works on the interval 1 to 5, right? So what did I say would be the best scenario to get the truest area possible? We said we would want the number of rectangles to become infinite, right? So can I just look at this expression now and let n go to infinity? Okay, let's try it. Let's see what happens. If I take this expression and I let n go to infinity, I'm going to take the limit. I'm going to let n go to infinity of that expression. Now, I don't want to rewrite the whole expression again, but think about what happens here. Think about what happens. So what happens, well, you know what? I will rewrite it. 16n squared plus 16n over n squared plus 64n cubed plus 96n squared plus 32n over 3n cubed. Okay, so at this point right here, all I did was distributed the constants through. I'm going to take the limit as n goes to infinity here. All right, my Cal 1 students better get this right. When you let n go to infinity, what do you get here? What over what?
Indefinite interval. It's indefinite.
Indeterminate. So you get, in this case, it's infinity over infinity, right? And so what can we do when we have infinity over infinity? L'Hopital. Sorry, L'Hopital's today a little bit, just a little bit. You can do L'Hopital. L'Hopital means you do derivative of the top and bottom. Okay? So what's derivative of the top? So I'm going to say on my next line equals by L'Hopital's rule. I know some of you have seen L'Hopital with an H in there. I always use an L. It's the same thing. Okay, limit n goes to infinity. By L'Hopital's rule, if I take derivative of the top, what do I get? 32n plus 16 over 2n plus over here, you have to do it again, right? Right? You have to do L'Hopital on that. It's infinity over infinity. Okay, if I do this though, what am I going to wind up getting? Look, I mean, this power and this power are the same, right? This power and this power are the same. Anytime you have the same powers like that on polynomials, you wind up just getting the leading coefficients divided by one another. I'm not going to go through L'Hopital. I have to do it several times on this one. At the end of it all, you should get 16 out front, yes? And then plus 64 over 3. And I'm going to get a common denominator here. 16 times 3. Come on, Robert. 90. 108? Is that right? No, what the hell?
16 times 3?
Yeah, I said 108. 48. Jeez, Robert. All right, plus 64 over 3. So what's that? No, that can't be right. Something's off.
112.
What's that?
Your 4.
Oh, I forgot the 4 out here. Oops. Yeah, thank you. Thank you. Yes, that's a plus 4. That 4 is going to stay. Okay, and it's going to matter here. Plus 4. Plus 4. So that should be 20, right? So 20 over 360 thirds. 124 over 3. Which is 41.33 repeated.
How about that?
Only for x squared, only on the interval 1, 5. So what method of exhaustion, right? Can you see? This is exhausting. This is actually a topic covered called Riemann sums. And there are some classes that you'll take where they will make you calculate a bunch of Riemann sums by hand. I know some of you have done them. It's fun, right? No, it's not fun. It's not fun. But it makes you appreciate just how powerful the theorem we're about to get is. This only works for x squared, only on the interval 1, 5. If I change the interval to go from -2 to 4, you've got to redo it, right? If I change the function from x squared to x cubed, you're going to have to change things. And if I change the function from x squared to, let's say, x sine x, you're going to be dead in the water because we relied on that formula, right? The Gauss formula, we relied on it somewhere in here. If you change these like trig functions, forget it. You can't do a Riemann sum. Riemann sums only work with power functions. So you have to be looking at like x or x squared or x cubed or something like that. So as great as it is, it still is very limited. Now there was a comment made earlier that this trapezoidal thing, did you do trapezoidal method or just write endpoints like this? Okay, so nobody has talked about this. Well, a little bit about trapezoidal, but let's go back to this picture. And let me draw this thing back. When I first started this, I said, let's look at breaking this up, right? And then let's go to the point to the right, go up, over, down, right? Up, over, down, right? Up, over, down, yes? But why did I pick the point on the right side of the triangle? Why not pick the point on the left side? Like, in other words, do it this way. Look, that's a little different. So in this time, instead of picking the right side and going up and over, I'm going to go left side, up and over, left side, up and over, left side, up and over. Wouldn't this still give you an area? But that area would be less, wouldn't it? Not more? So this would be an underestimate as opposed to an overestimate. Yes? But the thing is, it doesn't matter. Because when so right now we're estimating the area to be 37.4. It doesn't matter because when we let this thing get more and more rectangles, look at my estimated area, 40.6. It's still getting closer to 41.3. And if we let n go to infinity, you get the same thing. Or maybe you're like, okay, I don't want to use the right endpoint. I don't want to use the left endpoint. Instead, I'll use the middle point. So see this little rectangle? I could have done right up over. This time I did left up over. What about the middle? So take the interval, go to the middle, go up, and then spread out, yes? That would give you, this would be a pretty good method, wouldn't it? Because you get a little bit of overestimate, little underestimate. And so maybe that's a better way, right? But again, it doesn't matter because as you let these things go to infinity, you're going to get closer. Now you see this got close, it got close fast, didn't it? So this midpoint method worked faster than the other methods, but it doesn't matter. We're letting n go to infinity, and in the limit, they're all going to go to the same place. So there's another method called trapezoidal method where instead of drawing rectangles, you do trapezoids. So you go like from here up, and you connect those two endpoints together with a straight line. And you find a formula for the area of that trapezoid. That's what you're referring to. And yes, this would be a very, very fastly converging method. But the formula would suck to create it because, we're just using length times width for rectangles. This trapezoid formula would really be bad. And at the end of the day, what's happening is all our rectangles are becoming so narrow that it doesn't matter what method you use, all right? Left point, left endpoint, right endpoint, middle point, trapezoid, any point, it's gonna work, okay? All right. So then came along the major discovery. And that is that there is a relationship between that area and the antiderivative, which is what you've been studying, right? We've been sitting here like, I'm going to give you an integral, you go try and find the antiderivative, right? We spent all this time trying to figure out how to do it. Now let's see why, all right? So let's just for the sake of just seeing, we were just looking at this function on the interval 1, 5, right? And we wanted the area underneath it. Okay, so check this out. What's the antiderivative of that function? Antiderivative. Okay, so the antiderivative, I'm going to use capital F of x because that's what we use when we first started talking about antiderivatives. We said this is little f, then the antiderivative would be capital F, right? And we'd say this is 1/3 x cubed, and then what? Plus c, right? Okay, Now, here's the mind-blowing thing, all right? Watch. If I take this function, capital F, and I plug in the right endpoint of this interval, 5, and then subtract from that this function evaluated at the left endpoint of that interval, we're going to get something amazing. Okay, so let's see what we get. If we plug 5 into this, we would get 1/3. I'm going to put in brackets, 1/3, and then we have 5 cubed, right, plus c. And then we have minus, what, 1/3 times 1 cubed plus c. Yes? Agreed? Okay, what's 5 cubed? 125. So that's 125 over 3. And then this c and this c are going to cancel, right? And so you have just minus 1/3. And what is that? And that is 41.33. And that's not a coincidence. That is the fundamental theorem of calculus. That is the big deal. That means what just took us like almost 3/4 of the class to do one Riemann sum problem for one fixed little interval for one particular function. We can do any function on any interval so long as we can find the antiderivative. Okay? So, for the next part of this class, what we're going to do is we're just going to get some notation cleared up. Okay, when we've been working, so more notation. So all of that Riemann sum stuff was just to make you appreciate. I'm not going to test you on that. You're welcome.
Thank you.
Yes. So here's notation. We've seen this already. This is the notation we used in the very beginning of this antiderivative idea. And this was what we call the indefinite integral. Okay, that was the indefinite integral. So basically, oh, I forgot the dx, sorry. Dx. So when we wrote, something in here, dx, you would go find the antiderivative, you would say plus c, right? That's what we've been doing for weeks. Now we have some new notation. The new notation goes like this. Integral sign, ab f of x dx. So we've added something to the notation. And the thing we've added are these two things right here, a and b. Now these generally are going to be numbers. But this right here is called the lower limit of integration and this one right here is called the upper limit of integration. But it's only called upper and lower because on the integral sign, this one's on the bottom and this one's on top, so lower limit, upper limit. But in reality, these are the endpoints of our interval that we're looking at. So the picture that goes with this is that you have some function, little f, and you have a left endpoint, you have a right endpoint. And the area underneath here, the area underneath there, A, has something to do with the antiderivative of that, right? It has something to do with the antiderivative of this. So what we do is we say that this, how did we calculate the 41.3 again? We found the antiderivative, and then what do we do with it? we plugged in something and subtracted something else plugged in, right? So for us it was 1 and 5, right? Which one did we plug in first, the 1 or the 5? We plugged the 5 in first, and then we subtracted from that what we got when we plugged in the 1. So as a formula, what I'm going to do here is I'm going to leave a space here. Okay, just leave a space here. I'm going to do it this way. I'm going to write capital F of B minus capital F of A. What happened to that plus C when we actually did this subtraction? They canceled, right? So you won't have a plus C there. So this thing is called the definite integral. Indefinite, definite. And you're going to get a numerical answer most of the time. Sometimes you get infinity, but that's coming later. So this gives you like a definite numerical answer as opposed to this, which gave you a big family of functions, right? So at the end of it all, what this says, if you see two numbers here, what you're supposed to do is you're supposed to find the antiderivative of that, and then you're supposed to plug in the 2 points, b and a, and subtract it. And that answer will represent the area underneath that curve. So I left a space here because when we're doing definite integrals, there's kind of like this middle piece that we like to put in here, and you'll see what I mean by this when we do our next example. Just write that down. That's f of x, and then there's this thing we call an evaluation bar, and we put on the side, we put b on top and a on the bottom. All right, we have a little bit of time, so let's do a couple of examples, all right? Now, we're not proving the fundamental theorem of calculus in this class. We're not going to do the proof. I'm not going to sit here and take you through why this is, all right? I mean, I had to do it when I was in undergraduate school. I forget what class I did. I had to prove the fundamental theorem of calculus, and it's not a proof that we should be addressing in here, all right? The book does attempt to do it, and if you want to read on it, you can. We're just going to use it, all right? So let's do this. How about we take yeah, I was going to do that, but we can't. We'll just keep it simple right now. Now, I haven't pulled any sticks yet, but I'm going to now. And Jace, you're the first one. So my question is, can you explain just in words what the answer to this is going to represent? Okay, which is, is our answer to this going to be a function plus c, or is it going to be some numerical value? Okay, and that numerical value will represent what geometrically?
The dimensional function of that.
The what of that?
The function.
Well,
Rather than the area.
the area, right, between that function and the x-axis on the interval 1 to 6. Okay, that's what our answer is going to represent. Whatever numerical value we get is going to be the area between that graph of that function and the x-axis. So if we go, why don't you go find the antiderivative of that real quick while I graph this thing. Cool. It was x to the 4th minus 3x. All right, so you all have the antiderivative? Yes? Okay, so what I would do here is the next line I'd write is equals, and you remember how I had written up here f of x with this bar with a, b, and I said just wait until we do an example? What this does is it allows you at this point to actually write what the antiderivative is. Just figure out what it is and write it down. So the antiderivative of this is what? 1/5 x to the 5th minus 3 halves x squared. Yes? No plus c anymore. The reason there's no plus c is it's going to get subtracted out anyway, so we're not going to write it. And then here, we're going to put here on the bottom -1, and on the top we're going to put 6. And now what are we going to do? Plug in. Which one gets plugged in first? 6 goes in first. So I like to do it this way. I like to write 2 huge sets of parentheses. This is going to be what I get when I plug in the b, and this is what I'm going to get when I plug in the a. So b is 6, right, for us? So it's going to be 1/5, 6 to the 5th minus 3/2, 6 squared. And then here, 1/5 times -1 to the 5th, and then minus 3 halves times -1 squared. Bless you. Does everyone understand what I'm doing? Find the antiderivative, plug in the 2 numbers, and then that's it. Whatever you get here is the area between the function and the x-axis.
That'd be kind of wacky.
It's going to be messy.
Like it's like 7,776 over 5 is the first one.
Yeah. So watch. We can compute that. It's just algebra at that point, right? Just mechanics. If you go to Wolfram Alpha, check out what you can do here. You can see this. You can say integrate x to the 4th, right, minus 3x from -1 to 6. There it is. 1,502.9, or written as a fraction. There it is. Okay? All right. So very powerful, this fundamental theorem of calculus, because you can now find the areas, right, under curves. Any curve, so long as you can what? Any curve, so long as you can find the antiderivative, right? So long as you can find the antiderivative, you're in business. Okay, so what did we start class with? I started with a question. What's the area of a circle? Right? We all know it's pi r squared. I have just enough time. So let's start this over now. We know that an arbitrary circle centered at the origin has that as its equation, right? The radius of this circle would be what? The distance from here to here would be r, yes? Agreed? Now, if I wanted to, I could write this as a function of x if I could solve for y. Plus or minus r squared minus x squared, right? And let's just look at the positive one because that'll give me the top half, yes? And this I'm going to call my function f of x. So here's the idea. We are going to go and find just the area of that first piece. Okay? So someone's getting pulled on here. Ricardo. Yes? Okay. Can you tell me the integral that I need to do? Like, what's the integral? What's the setup? So I'll start you out. There you go. Okay, so what function are we integrating? What function are we looking for the area underneath? Square root of r squared, okay, dx, right? X is our variable, okay. What are the limits of integration? Where are we going to start and stop?
From 0 to 1.
0 to r, right? 0 to r. Everyone see this. Remember, r is a constant, right? If someone says, hey, what's the area of a circle of radius 4? Then 4 is given to us, right? But we're trying to find a formula in general. But r would be provided, yes?
Yep.
Okay, everyone got that? Good. Jeremiah? Jeremiah, any idea how to integrate this?
Don't we have a formula for that? I don't know, that won't work. Okay. Can we do 1/2 r squared minus a squared? Like 2 to the 1/2?
All that to the half? You could. But when you see the square root of something squared minus something squared, do you think anything in particular? You don't think trig sub?
Oh, yeah.
Trig sub, yes? Right? Trig sub. Trigonometric substitution. There's 3 different things we look for, right? It's either like square root of a squared minus x squared, or square root of a squared plus x squared, or square root of x squared minus a squared, right?
Should be r secant theta.
So for this one, r is like the a, isn't it? R is like the a. And so what would be the trig sub that we make here? Jeremiah, do you know the trig sub you make? Arafat? Trig sub? Which one? What's a trig sub? R sine theta. Everyone agree? R sine theta. Okay, and then from here, we know that the derivative of this, r cosine theta d theta, and the square root of all that stuff, what would this become? R cosine theta, right? Okay, now, I'm ready to integrate, right? I'm ready to integrate. But remember, this is a definite integral now, right? So it has these limits. So what I'm going to do is I'm going to do all this. I'm doing basically all this work on the side, and I'm doing it as an indefinite integral. So I'm going to do all this, and I'm going to figure out what the antiderivative is, and then I'm going to come back here and plug it in, do the 2 endpoints, and figure out, right? Okay, so let's rewrite this integral. The square root gets replaced with r cosine theta times, and then the dx is r cosine theta again, d theta. And we've seen cosine squared so many times now, it's just like, it's actually kind of boring us now, yes? Can I pull r squared out? Yes, r squared is a constant. So r squared can come, oh, pi r squared. Are we supposed to get pi r squared? Okay, and then I have cosine squared theta, d theta, right? All right, so now to do that, Gina?
The power reducing?
Yeah, power reduce, right? You pull the half comes out. Oh shit, wait, pi r squared, okay, maybe it'll all work out. Okay, integral, right? So now you have 1 plus cosine 2 theta d theta, and now you go and integrate each of those, right? Well, maybe, oh wait, hold on. Yeah, that's right. Yeah. Integrate. So half r squared, and then now the antiderivative. So theta plus 1/2 sine 2 theta, right? And then we would normally say plus c. If you want to do it now, fine, but you know, we're not going to need it because it's going to be a definite integral. Everyone, yes, we've done that so many times now? Okay, we got to get from theta back to x, yes? And we've done this so many times also, right? This is really just going to turn into sine theta, cosine theta. And maybe we need a triangle. Do we need a triangle? Yeah, we should do a little triangle here. This is theta. Sine is what? X over r. So this should be x, this should be r, and this side is the r squared minus x squared. So here's where we are. This is equal to 1/2 r squared. Okay, what's theta? Yeah, so we have to solve this for sine theta, then take arc sine on both sides. So arc sine of x over r. And then plus, okay, we need sine theta times cosine theta. What's sine theta? X over r. And what's cosine theta? Square root of r squared minus x squared over r. Okay. Yay or nay? Okay. This is the antiderivative. Now what we need to do is evaluate it at the two endpoints. Okay, so I'm ready to finish writing this step right here. Okay, this right here, okay, this becomes this expression, 1/2 r squared arc sine of x over r plus x over r times square root of r squared minus x squared over r, evaluated at the two endpoints, which are 0 and r. Right? 0 and r. Which one goes in first? Which one goes in first? R. Okay, so again, I like to write two big sets of parentheses when I do this. R is going to go in first. Jordan's not here, I don't think, right? No, Jordan? Oh, weren't you sick? No? No? Was that last week? No? No, okay. Well, go ahead. You're here. So, okay, so we're going to plug R in, right? We're replacing what with R? In here? The X with R. Okay. Y'all ready for that, everyone? Okay, Jordan. So we're going to have 1/2 r squared. Okay, parentheses. Sine inverse of 1. So that means at what angle is sine 1? Pi over 2. Right? When you replace x with r, you get r over r. Arc sine of 1 is saying, where is your y coordinate 1 on the unit circle? And that's straight up. That's pi over 2. So when you plug in r into this, you get pi over 2. Okay, plus, now, r here, right? 1. R squared minus r squared. So r squared minus r squared, 0. That goes to 0, which kills this whole term, right? So all you're left with there is what you had out front. I'm going to put the 0 here, but, okay? So we had the 1/2 r squared. This became pi over 2. That was 0. Okay, then we do minus. Now, Luis? 0, right, for x. So 1/2 r squared, that stays. Okay, so at what angle is your y coordinate 0? Yeah, but we're in arc sine, so you can only be like over here with arc sine. So your y coordinate is 0 at 0. Or 2, well, you can't come all the way around. So 0, just 0, just 0. Okay? So everyone agree that arc sine of 0 is 0. Okay, 0 plus, now over here, replacing x with 0 over r is 0, right? And that doesn't matter anymore. So that's just 0 here. So this whole thing's gone, isn't it? Because it's 1/2 r squared times 0. So that whole thing is gone. And so all you're left with is 1/2 r squared times pi over 2. Shit, this isn't the answer. Wait, that's not the formula. Remember, we only did one quadrant, right? That's only a quarter of the answer, right? Remember that? We only did this. So the true area is 4 of those. So multiply that times 4, and what do you get? Pi r squared.
So why couldn't we just take the formula and divide
Boom.
by 4 in the beginning?
Pardon?
Why couldn't we take the formula and divide it by 4 in the beginning?
What formula?
Pi r squared. Area equals pi r squared divided by 4 to get 1 quadrant.
Yeah, but we didn't know, we were acting like we don't know the formula for the area. So look, before your eyes, right before your eyes today, we have shown where this formula comes from. Do you all see that? And we used, what did we use for that? Well, we had to understand definite integral, right? Understand areas. And then we had to know how to integrate. Is there a question? Yes.
Could this potentially be like a bonus question?
Are you wanting this to be a bonus question? Is that what you're asking? Do you think that's bonus worthy? Do you think that's a bonus worthy question?
I mean, it takes a while.
I don't think the trig sub in that is any harder than a problem in the test would be, right? That I think is what's so nice about it, is that we actually get this is not that much work, but,
Rely on trig.
pardon?
We already have to have like trig knowledge, right?
Trig knowledge,
Yeah, we had like use.
sine and cosine,
Yeah.
yes. So, yeah, I'm getting to it. There, that's, so I'll get back to your statement here in a second. All this is, these are homework assignments you've already done, okay? Those are homework assignments you've already done, but I told you to ignore the numbers. Remember I said ignore the numbers on the top and the bottom? Now all you have to do, in theory, is get your answer and evaluate it at the two endpoints. Subtract the answers and see if it matches the back of the book. But you might want to just run through them again. It won't hurt you to just go through the whole problem again. This time just doing one additional step at the end. Okay.
It's definitely bigger than what we did in Cal 1.
What's that? Yes. Let me turn my camera off.